Okay, so my name is Yaron Shulamy, and I'm going to present a work that was done with Daniel Sigalov named Weighted Information Filtering, Smoothing, and Out-of-Sequence Measurements Processing. The outline of our talk is going to be motivation and background, problem formulation, main results, numerical example, conclusion, and future work. But before I begin, let's take a look at some classical problems in the Bayesian state estimation field, all of which have similar form of previous state plus gain times innovation. But in each problem, the gain is computed differently. Here we can see the classical Kalman filter, and here we can see the fixed leg smoothing with the different gain. And out-of-sequence measurements problems have similar form and even more complicated structure. And in the general case, the standard solution requires an approximation and is no longer MMSE optimal, while optimal solutions require state augmentation. So the bottom line in the Bayesian setup is that every problem requires a unique algorithm, and some problems require us to sacrifice optimality. And why is this the case? Because of the process noise that is used to cope with model inaccuracies, but it complicates stuff and it correlates with past measurements, which prevents optimality of standard solutions. And the question that we are asking is, what if we could have a unique optimal algorithm for all? So in this video, we are looking at an estimation example. A target moves in space, measured and estimated. The blue line indicates the ground truth. The red and cyan dots indicate the measurements, red for in-sequence and cyan for out-of-sequence measurements. The bouncing crosses represent the measurement's arrival time, and the green line is our estimation. And although the target moves in different ways, we can see that our estimation remains pretty accurate. And by the end of this presentation, we will try to convince you how simple this estimator is. Now, I would like to present a bit less known filter named Savitzky-Golay. This filter has a deterministic modeling, and it is actually a polynomial fitting of noisy data that usually operates in batch mode. And as you can see in this graph here, while the Kalman filter in the black line has a state, and every time a measurement arrives, it updates the state, the Savitzky-Golay filter in the green line takes all measurements inside our window and fits them all together into a curve, which means that the estimation is not for one point in time, but for every point on this curve. And Savitzky-Golay experts know that it is more accurate at the middle of the window and that the accuracy decreases when going to the sides. And maybe this is why people who try to estimate target in real time are less familiar with the Savitzky-Golay, since it is less accurate at real time. So the main idea of this work is to combine the recursive property of the Kalman filter with the deterministic formulation of the Savitzky-Golay with proper information handling. So now we are ready to formulate the problem. Here we can see the exact same dynamical equation as in Kalman filter that can take our state from time from TL to TK, which we can also write in a reverse form to take our state from time K to time L. And we also have the Gaussian measurement model, again, the exact same one as in Kalman filter. And the only difference between our filter and the Kalman filter is that here we have no process noise, but we will get to that in a few more minutes. So our goal is to derive an estimator of the state using the weighted least squares criteria. And in our case, we are talking about a sum of normalized square differences between the measurement and the state projected on the measurement time and space. W is a weighting factor reflecting the effect of measurement L on xk, and it is important to note that unlike the standard formulation of Kalman filter, here all measurements measure the same xk, and this is done by applying the dynamical equation on xl. This is xl. So now when we're left only with xk, the optimal estimator in the weighted least square sense is shown here. Well, this is the state estimation and the covariance approximation. And this is without elaborating about W, so that's what we're going to do next. So W can be any positive function versus time. For example, this is the rectangle kernel, which tells us that every measurement inside our window receives a weight of 1 and the others receive a weight of 0. And the most interesting thing about this kernel is that if we also apply this R and this H, then the algorithm becomes identical to the Savitsky-Golay solution, which means that the Savitsky-Golay is a special case of our filter, and unlike standard application of Savitsky-Golay, it can be extended to general measurement models, which means general R and general H. So at this point, we can keep talking about a few more kernels, but in order to extract the relations between our filter and the Kalman filter, let's review the next example. This is the exponentially decaying kernel, and the most interesting property of this kernel is that it allows us to write our estimator in a recursive form. So if W satisfies these three statements, like the exponentially decaying kernel, then the optimal state has the following recursive structure. While here we can see the previous state fused with the new measurement in order to get the new state. And the same goes with the covariance. So by utilizing the W as the exponential kernel, we obtain the EWIF, exponentially weighted information filter. And in this form, we can try to compare it with the original Kalman filter, which also has a recursive form. So at first sight, it was hard to compare between the two filters since the original formulation of the Kalman filter looked different from the EWIF. But using the information form and some mathematical manipulations, the Kalman filter became a lot more similar to the EWIF. And here we can see that the actual only difference is that the Kalman filter has a process noise covariance added to the old state covariance before fusing it with the new measurement. And in the EWIF, the old state covariance is inflated by this exponential factor. This factor controls the trade-off between historical and new data, while the tau is our intuitive parameter to allow the users to choose how smooth they want their estimation to be. So if we take tau to infinity, then all measurements have equal weight, which gives us the exact same solution as Kalman filter with 0Q. And if we take tau to 0, then all weight is on the latest measurement, which gives us similar results to Kalman filter with very large Q. Then we try to compare the performance of the two filters just to see that we're on the same page. And in this example, we have found pretty similar results. But the main purpose of this work is not to compare the EWIF with the Kalman filter, but to find a generalization and simplification of the estimation process. And this led us to realize that only the multiplicative uncertainty inflation allows for generalization of previous results. So for W satisfying the assumptions, the optimal estimator is given by this formula. While here, YD is valid for an arbitrary time prior or equal to real time, and XM and XL are optimal at any arbitrary times. And this is a big step, since with this formulation, filtering, prediction, smoothing, and out-of-sequence measurements are treated identically and optimally. Okay, this brings us to our final example. Here we have 4 different filters, 2 of which include the out-of-sequence measurements and the others don't. 2 of them are filters in real time and the others are fixed leg smoothers with 1 second delay. And the strongest statement of this example is that all of these 4 filters came from the exact same formulation of the EWIF, and that in the Bayesian setup, each one of them had to have a different formulation. We can also see that the green estimator is the most accurate one during the scenario, and this is not surprising since it has the most information at the estimation time. And last thing to note is that the measurement properties are changing in time during the scenario by noise amplitude, frequency, and delay, but all of these 4 filters work as expected without the need to change any parameter. Okay, you can also find a link for this example in the article. So to conclude our work, we derived a general estimation method. Model uncertainty is treated by applying exponentially decaying weights to the measurements. Recursive solution exists, clearly related to Savitsky-Golay and Kalman filter, allows simple, unified, and optimal treatment of filtering, prediction, smoothing, and out-of-sequence measurement problems. Here are some more desirable properties that were not mentioned in our presentation, but we can also say that measurement noise covariance is only needed up to a scaling factor. No extra storage or measurement reprocessing is needed when we deal with out-of-sequence measurements. And out-of-sequence measurement removal is as simple as out-of-sequence measurement incorporation. And in our future work, we are planning on obviously comparing our filter to all Bayesian methods, dynamically changing tau, multiple tau hypotheses, alternative to IMM, with in the presence of clutter, and track fusion. Thank you.